Okay, we're back. Last time we talked about what an electric field is. It's the alteration of space created by an electric charge. We also talked about the shapes of electric fields around different charges. Here's the shape for a circular or for a spherical positive charge, spherical negative charge, two positive charges, two negative charges, a positive and a negative charge, and finally the field between what are called parallel plates. Okay. Today, what we're going to talk about is not so much the shapes of the fields anymore, although we will talk a little bit about that. We're mainly going to talk about how to calculate an electric field, so some of the calculation stuff that we'll be doing. Okay, let's get started. So, the magnitude of an electric field, the size, is based on the size of the charge creating the field, not on the test charge. Let me explain a little bit about what this means. I'm going to go back to that other page. We figured out the electric field shapes by imagining that there was a test charge, a little tiny positive charge, like a proton, somewhere near this spherical positive charge. And the electric field lines, we knew how to draw them because we said that they would be in the same direction as the electrostatic force would be on that test charge due to this object. Okay? So, when we talk about the electric field, this electric field exists even if that test charge isn't there. So the size of the electric field is only dependent on the size of the charge creating the field, not on the size of a test charge that might be in the field. So the electric field is only based, the size of it, is only based on the size of the object that creates the field. Once a test charge is placed in an electric field, it gets subjected to an electrostatic force. Now that force, however, is based, think about the equation for force, for electrostatic force. It is listed right here. Fe equals K Q1 Q2 over R squared. That has both charges in it. The size of the force is based on both the size of the test charge and the charge creating the field. Okay, so the electrostatic force, just to sum this up, electrostatic force depends on the magnitude of the two charges interacting, whereas electric field strength depends on the magnitude of the charge or charges creating the field, not the test charge, not the charge that we say is in the field, not the charge that is experiencing the field and reacting to it. We're just talking here about the charge. The electric field the size of the electric field is determined by the charges that are creating that field in the first place, the charges that are creating those patterns. Now, the equation for the magnitude of an electric field is given in the reference tables. It's the second equation down on your reference tables under electricity. E, standing for electric field strength, equals Fe over Q. Okay? Which can be rewritten if you want to. Imagine we just cross-multiplied. Fe equals the electric field times Q. Now let's talk about what this Q is for a second. Okay? This Q, let's see here. Hold on, I might be getting ahead of myself. Okay, so this Q here, I know I just got done saying the electric field size depends on the magnitude of the charge creating the field, not the charge in the field. This Q in this equation is the Q for, I believe, the test charge. Okay? Because it's like saying the electric field strength is equal to the electrostatic force divided by the test charge. Well, the test charge is already included in the electrostatic field, or the electrostatic force equation. So if we divide this by the test charge, it's kind of like we're removing the test charge from the equation, okay? It's like we're saying, okay, take this, which is based on the test charge, divide out the test charge. What you have left is called the electric field. We'll get more into that as we do more examples. The units of this, if you look, of electric field strength should be Fe, would be newtons over coulombs, N over C, okay? Electric fields are obviously vectors since we've been drawing them as vectors. Again, I'll just make a little note here that Q in this equation is the test charge. It's the charge that experiences the field. That charge is adding nothing to the field. It's experiencing the field created by other charges, okay? As far as these units go, okay, why do we study electric field? Think of it like you would think of like a unit price at a supermarket, okay? You might go buy something in bulk at BJ's or Walmart or some other store like that, and they give you a price, but they also tell you the unit price. You know, if it's, let's say, $200 for, or, well, that's a bad example. Let's say it's $2 for, I don't know, a 4-pack of something. Then you do in your head the math, you say, well, if it's $2 for a 4-pack, that means each one individually is 50 cents. So with electric field, what you should be thinking of this as, think of it kind of like a unit price. It tells you how big the force will be on the test charge, on the object in the field interacting with the field, depending on how many coulombs of charge that object has. If that object has a bigger charge, there's going to be a bigger force on it, okay? So that's what an electric field shows you. It shows you the amount of newtons per coulomb that will be subjected to any charge inside that field. Okay? Think of this as the ratio of size of electrostatic force to the magnitude of the test charge. In other words, the force per unit of charge. Now, I am going to show you one more equation that's a little bit more advanced. It's actually not in your reference tables, but it's easy enough to figure out how it comes about. Let's start with our equation for electric field, Fe over Q. Well, we know that Fe is really K, Q1, Q2 over R squared. And we're dividing that whole thing by Q. Now, remember, this Q is the test charge, and the test charge is also one of these, Q1 or Q2. What that means is that the electric field could also be given for a spherical distribution of charge by this equation, E equals KQ over R squared. But, just note, in this equation, Q is the charge creating the field. So, you don't really have to use this equation ever. I thought it would be good just to see it though, and know that this is a legitimate equation as long as you know that this is only used for a spherical or point charge, and that Q in this equation is the charge creating the field. Here, Q is the test charge. I'm anticipating most of you will be using this equation for calculating electric fields. Okay, enough talk. Let's get to some examples. Number one, the Van de Graaff generator. I'm really sorry that you guys are not in school to see this. The Van de Graaff generator is that thing that you've seen before that can make people's hair stand up and shocks you if you touch it. It's a lot of fun to play with. We usually spend at least 20 minutes playing, or 15-20 minutes playing with it in class. Everyone usually has a lot of fun with it. I promise if we go back to school, no matter where we are in terms of curriculum, we will spend some time playing with the Van de Graaff generator. The way it works is it actually builds up charge on its outer shell, okay? And in this case, I think I got this from the specs for our actual generator. It can collect up to 8 times 10 to the 6th coulombs on its outer shell. what would the magnitude of the electrostatic force between the generator and a proton 0.3 meters away be? Okay, we're looking for electrostatic force. So that's Fe equals K Q1 Q2 over R squared. K, we remember from the reference tables, is right here. 8.99 times 10 to the 9th newtons times meters squared over coulomb squared. Q1 is one of the charges we're dealing with. We're dealing with the charge that's on the generator itself, as well as the charge of the proton that's 0.3 meters away. Let's do the charge on the generator. By the way, 8 times 10 to the negative 6 coulombs, even though it's 10 to the negative 6, just let me tell you, that's a huge charge. We're talking easily trillions or quadrillions of extra electrons here. Charge of a proton is the same as one elementary charge. Okay, protons are have the same, an elementary charge is either a charge of a proton or charge of an electron. In this case, 1.6 times 10 to the negative 19th coulombs. And that proton is 0.3 meters away from the center of charge for the generator. We can calculate this, very easy. 8.99 e to the 9th times 8e negative 6 times 1.6 e negative 19. Oh my gosh, you guys almost let me forget. I need to square that. Let's see, divided by 0.3. We need to square that and the parenthesis, and we end up with a force of 1.28 times 10 to the negative 13th newtons. Now, that seems like a really small force, but just hold on to that for a second, okay? Let's go and find the magnitude of the electric field created by the charge on the generator. So the generator charge is the one creating the field. That means the proton is our test charge. That's the charge experiencing the field. We're concerned with the charge that is created by the generator. So that means if we want to find the electric field, that's E, and we know that the equation should be Fe over Q, where Q is the test charge, the charge experiencing the field. We already know that the electrostatic force is 1.28 times 10 to the negative 13th newtons. That's the force between the generator and the proton. And the proton, which is the charge experiencing the field, the charge moving around in that field, not the charge creating the field, has a charge of 1.6 times 10 to the negative 19th coulombs. I can divide these two, and I get approximately, granted with some rounding, that we'll just say that's 800,000. That was the point of this problem. 800,000 newtons per coulomb. Okay, that's the electric field strength, and that is regardless of what the test charge is. Because think about it like this: you might say, "Oh, well, but if you changed how big the test charge is, then shouldn't that change the electrostatic field or the electric field?" Well, no, because if we change the test charge, then the electrostatic force is going to change as well, and it'll change in such a way that the electrostatic field or the electric field will still be the same, 800,000 newtons per coulomb. So what this ultimately means is that the force, if you were to have 1 coulomb of charge outside of that generator, because of the charge that's on the Van de Graaff generator, it would experience 800,000 newtons of force. If you had half a coulomb, it would experience half that much. That's why the electric field is so useful. It can make it very easy for us to predict, okay, well, how big is the force on this charged particle going to be? Okay, a couple more things. C, if this electrostatic force is the only force acting on the proton, at what rate will the proton accelerate? Well, if it's the only force, that means it's the net force, right? The net force is equal to Fe, and we know net forces are equal to m times A. So if Fe is 1.28 times 10 to the negative 13th newtons, well, the mass of a proton, wait a sec, that's on my reference tables. The mass of a proton is 1.67 times 10 to the negative 27th kilograms. I should be able to solve for the acceleration. And some of you are probably saying right now, wait a second, just given these numbers, this looks like it's going to be an obscenely high acceleration. And you're right, it is. It's approximately 7.66 times 10 to the 13th meters per second squared. That's a ridiculously high number. But you have to imagine that force, even though it's small, look at the mass it's getting put on. That mass is tiny. Kind of makes sense this acceleration should be so big. Okay? My last question, and that's what you'll see with these very small subatomic particles. You'll see huge accelerations for them a lot of times. Last question for this video. An electron is subjected to an electrostatic force of 5 times 10 to the negative 15th newtons. What's the magnitude of the electric field causing the force on this electron? Straightforward, E equals Fe over Q. The force is 5 times 10 to the negative 15th newtons. Just like with the electrostatic force equation, we're not going to plug the negative charge in. We're just going to do the magnitude of the charge. An electron has the same charge as an elementary charge, because it is an elementary charge. So that's 1.6 times 10 to the negative 19th coulombs. And we get an electric field of 31,250 newtons. Meaning, if you had 1 coulomb of charge in this field that's getting created by some unknown charge, it would have 31,250 newtons of force placed on it. So notice here that we don't even know the other charge that's creating the field, okay? We're just told, here's an electron, here's how much force it's experiencing, we can figure out how big the electric field is on it. Next time we'll do some more examples.